Hello everyone, I will teach you van der Waals equation of state and compressibility in this tutorial. And we will solve some problems which were asked in GATE and engineering services on this topic. I am Lakhan Lal and this is my profile. I will be teaching you thermodynamics in this series of lecture. These lectures are particularly helpful for GATE Mechanical, GATE Engineering Science, and SSC JEE Mechanical. So I hope you will enjoy these lectures. And if you have any doubt, you can mail me or you can make comments. So first, let us come to the van der Waals equation of a state. So ideal gas equation fails at some point. Ideal gas equation is derived based on some assumptions that the gas molecule has no volume. It is just a point, right? And the intermolecular interaction between the molecules is negligible. So these two are important assumptions of ideal gas equation. But for real gas, these two assumptions are not, are false for real gas. Real gas molecule has some volume and there are some interatomic interaction between them. So at high pressure, your ideal gas equation doesn't remain valid because intermolecular interaction becomes high. When you force gaseous molecule in a closed space at high pressure, intermolecular interactions become significant, more and more significant. So your ideal gas equation fails at that point. And at low temperature, you have low kinetic energy, and due to that, the molecules have enough time to interact. So at these two points, ideal gas equation fails. So we have to modify it in order to use it for real gas. So first modification is for excluded volume. We assume that the real gas molecules have some volume which is known as excluded volume. So the volume space available for those molecules is less than the container volume. So you have to minus a term NB from the volume container volume. So your equation will be something like P into V minus NB is equal to nRT, right? And P into V, a small v is your molar volume, meter cube per mole. So when you divide this by N, you will get this. So in terms of this, you have the equation will be something like this. And the second modification is for attractive and repulsive force between molecules. Basically, it is for van der Waals attractive force, right? So due to that attractive force, the pressure you measure is always going to be less than the ideal gas pressure, because in ideal gas, the pressure is quite less. The pressure is quite less. So they have large separation distance between their atoms or molecules. So they have large separation distance. So that's why their intermolecular interaction is negligible. So they can exert more pressure. But for real gas, there are some significant interatomic intermolecular interactions. So the pressure you measure is going to be less than the ideal gas pressure. So you need to add a term AN square divided by V square, AN square divided by V square to pressure term. So you will get this equation. And if this equation is written for 1 mole of substance, you are going to have this equation in terms of this. And again, this V is going to be molar volume, because this N square will come, below this V square, and you will get this equation something like this. Some molar volume V. Again, let us come here. So this is your van der Waals equation of a state. This term accounts for attractive force. This term accounts for, this B accounts for what? Your, volume of the gas molecule. And these A and B, these two constants are basically characteristic constant. It is different for different gas. So now we can expand this. Just multiply the term P into B like this. So you just have to expand it. So you will get the cubic equation like something like this: PV cube minus B square, PB plus RT plus AB minus AB is equal to 0. So for any given T and P, we will have 3 values of molar volume. Please keep this in mind. For any given T and P, this is a cubic equation for V, PV cube minus B square. So you have T, V, P. So for any given T and P, if we solve this equation, we will get three values of molar volume, right? And at critical point, if you remember this, it is the point where we cannot differentiate between gaseous phase and liquid phase, right? We cannot differentiate it. It is just a point on a vapor dome. So at that critical point, P becomes equal to P critical, and your temperature is also going to be T critical. So we will solve this equation, and we will get root V is equal to Vc. Now at critical point, if you draw a horizontal line, right, it is going to intersect the vapor dome only at one point. So you cannot going to get 3 different values of molar volume, right? You are going to have only one volume, one value of molar volume, which will satisfy this equation at critical point. So if you have, so in that case, your equation is going to be something like this: Pc into V minus Vc whole to the power cube. This is whole to the power cube, not just V minus Vc cube. No, whole to the power cube is equal to 0. So you will get 3 different roots. No, 3 same root. V is equal to Vc for this. Now compare this equation 1 and 2, this equation and this equation. Compare these two. So you will get this V cube C is equal to AB divided PC, 3V square C is equal to this, 3VC is equal to this, right? Okay. So solving this, you will get Vc is equal to 3B, PC is equal to A divided by 27B square, and Tc is equal to 8 divided by 27 A divided by Rb. Okay, so please keep this in mind. Vc is equal to this. These are the critical parameter: critical volume, critical pressure, and temperature, critical temperature. So these parameters were evaluated in terms of characteristic constant A and B. So see, this is your vapor dome, and you see these lines are isotherm. This curve is isotherm. This curve is isotherm. Temperature remains constant on this line, and these lines are coming like this. And in between the vapor dome, this is going something like this. Temperature remains constant during phase transformation. So it is going to be something like this, right? But this is based on the real, what you call ideal gas equation. But if you are coming to van der Waals equation of a state, and the equation we derived from that state, van der Waals equation of a state, which used to be a cubic equation in terms of V cube, right? We derived just one slide ago we derived this equation in terms of V cube. So V cube, and in terms of pressure and temperature. So for a given temperature, a constant temperature, we are going to have a relation for P and V. So we can draw a curve known as isotherm. So at different temperature we are going to have different isotherms. So these are isotherms based on the van der Waals equation of a state. So for given pressure and temperature, we know that we are going to have three different real roots, three different real molar volumes. So we can say here like this: if we draw a horizontal line, okay, so an isotherm is going to intersect it thrice. See, like this, it intersects here, here, here. So it is going to intersect something like this, right here. So for this isotherm, you are going to have three different molar volumes. Again, for each and every isotherm, you will get something like this, three values. But see here at critical pressure, the isotherm is just touching this at critical point. And if you notice it, if you check this from upwards, from over this in the direction of arrow. So before C, it is going to be a concave shape, and after C, it is going to be a convex shape, right? So it means that at point C, the curve is changing its slope. So the point C must be a point of inflection, because curve changes its sign here, right? So, and it's just touching the curve, just touching the vapor dome. So you cannot get three different volume at this point. In a speed, you will get three same volume V. You will get here twice, right? So this is just showing, again it is just same thing, it is showing. So this diagram is taken from the book Thermodynamics by Enrico Fermi. Now, if we take VC, PC and TC, okay, as the unit of volume, pressure, and temperature. Okay, so like say if you have critical temperature of 100 degrees centigrade and the actual temperature of the gas is, say, liquid is 150 degrees centigrade. So we can say that its temperature is, its reduced temperature is 1.5, means its actual temperature is 1.5 times of its critical temperature. So we can define its temperature in terms of its critical temperature. We can define its pressure in terms of its critical pressure. We can define its volume in terms of its critical volume. Right? So this is the meaning of the parameters like reduced pressure, reduced temperature, reduced volume. So these parameters are unitless. P divided by PC, T divided by TC, these are unitless. So if we put these parameters in van der Waals equation of a state, the equation of a state becomes unitless. Right? So put this in the van der Waals equation of a state, and we have already derived the values of Vc, critical parameters like Vc, Tc, and what? Your PC, critical pressure, in just 2-3 slides ago. So Vc is equal to 3b, PC is equal to A divided by 27b square, and Tc is equal to 8 divided by 27a divided by rb. So put this in equation, van der Waals equation of a state, right? So we will get, okay, put this in equation, this equation. We will get van der Waals equation of a state in terms of unitless and reduced quantity, TR, PR, and VR. Okay. And again, you will notice that this equation is, this is free from A and B, which is used to be characteristic constants. So this is free from that, means this equation can be applied to any gas. So now see here, PR plus 3 divided by V square R into VR minus 1 by 3 is equal to 8 by 3 TR. It doesn't have any terms containing A and B. So since it contains only numerical terms, it is same for all substance. The state of various substances which are defined by some same value of PR, VR, and TR are called corresponding state. And principle of corresponding state says, now this is quite important. Principle of corresponding state. So the state of various substances which are defined by same value of PR, reduced pressure, reduced volume, and reduced temperature are called corresponding state. This state is known as corresponding state. Okay, so this is your corresponding state. Now what is principle of corresponding state? It is quite important. The question is asked on this. It says all fluids when compared at same reduced temperature and reduced pressure have same compressibility factor Z. Right? When compared at same reduced temperature and pressure, it has same compressibility factor Z. So say any two gas, if they have same reduced temperature, same reduced pressure, so they are going to have same compressibility factor Z. So it's an important relation. Again, see compressibility. So at low pressure, ideal gas relationship is valid. Okay, low pressure and high temperature. At higher pressure, use of ideal gas equation may lead to error. To express more accurate relationship between variable P, V, T, pressure, volume, and temperature, a correction factor, gas compressibility factor denoted by Z, is introduced in ideal gas equation. right? So this compressibility factor is basically a measure of what? How much the behavior of the gas deviates from its ideal behavior. If it deviates more, then compressibility factor is going to be more. I mean less. And if the gas behaves ideally, then the compressibility factor is going to be 1. And if it behaves non-ideally, then it is either less than 1 or greater than 1. So it was observed during the experiment that the ideal gas law can adequately predict the behavior of gas, low pressure and high temperature. Product of pressure and volume is different for different gases at higher pressure but same at low pressure density because intermolecular interactions are negligible because of large separation distance. Okay. Now come to this. Z is equal to, what is this compressibility factor? It is equal to what is the actual volume of the gas. Okay. What is the actual volume of the gas occupied by gas, and divided by the volume we predict from ideal gas equation. So Z is equal to V actual divided by V ideal. Now we know V ideal, PV ideal is equal to nRT. Okay. So just put V ideal is equal to what? V actual divided by Z. So you will get something like this. Okay. And if you divide V actual by N, you will get molar volume small v. Molar volume means meter cube per mole. Then you will get this, and you will get Z is equal to PV, where V is molar volume. So PV actual divided by RT, where R is your universal gas constant. Now keep this in mind, that R universal is 8.314 joule per mole Kelvin. T is your absolute temperature in Kelvin. P is equal to pressure in Pascal, and V is your molar volume. If R is 8.314 kilojoule, then it is going to be kilomole per kilomole. Now ideal gas equation fails at where it fails. At high pressure, when you force the gas to interact with each other, and at low temperature, if they have sufficient time to interact with each other. Okay, so it fails at that point. This slide we have already covered. Now come to some questions. This question was asked in GATE, I think 17. It says the van der Waals equation of a state is given by this equation you have given. You have the equation where P in bar B. Okay, for A the constant A and B, value of A and B was given respectively. Air is contained in a system at 160 Kelvin and 0.08 meter cube per kilomole. If P1 is the pressure calculated using ideal gas equation of the state, and P2 is calculated using van der Waals equation of the state, then P1 by P2 is equal to. So first what you do, you calculate the pressure using ideal gas equation. Ideal gas equation is equal to PV is equal to what? nRT. Okay. So volume is given in terms of molar volume. So PV is equal to N is equal to RT. So you have everything you have. You just find out this P. And then everything is given. You just find out P2 using this van der Waals equation. A and B you have, V you have, R universal you have, everything you have. You have to just find out this V. Okay. The value of R universal is going to be, actually you should remember this, 8.314 kilojoule per kilomole Kelvin. Okay. So the answer is A, 1.78. You just solve this problem, it's quite easy. Now come to this. For a gas obeying the equation of a state given by P plus A V square into V RT, the value of critical volume and critical temperature are these: 0.004 meter cube per kg, 100 degree and 100 degrees centigrade respectively. If value of the gas constant is 250 joules per kg Kelvin, then the value of the constant A is. Note that the critical point is the point of inflection on the critical isotherm. So critical values are given, like critical volume and critical temperature, and you were asked to evaluate the value of A. Okay, and it is given here that the point, what is point of inflection? The critical point is point of inflection on the critical isotherm. Okay, it is given, but you already know that point of critical point is actually the point of inflection on isotherm. So critical isotherm, so which is passing through the critical point, where the curve changes its slope, that is called point of inflection. So if the curve changes its slope, then the slope of the curve should be 0 at the point of inflection. Then only it can change its slope, right? This is what we used to do in maxima and minima in basic calculus class. We used to do this. So for doing that, you just differentiate the equation of curve and equate it to 0, and you used to get if it is 0, then you are at point of inflection. The same we will do here. So just expand this like this, expand this, and you will get pressure in terms of this. You just differentiate pressure with respect to volume at constant temperature, so you will get this, equate it to 0. When you equate it to 0, everything you have, R you have, T you have, V you have, so you will get the volume of value of A here. So A is 186.5. Everything is in SI unit, so you will get like this. So answer is this. Again, water vapor can be treated as an ideal gas for all temperature and pressure for sufficiently low temp. So here you can read, okay, it is clear from this figure that at pressure below 10 kilopascal, water vapor can be treated as an ideal gas regardless of its temperature. Okay, regardless of its temperature. And we can see in this figure that below 10 kilopascal, the error is 0.1% only. So we can treat the water vapor as ideal gas. But beyond this pressure, the error is significant. So we cannot treat the vapor as ideal gas. Now come to the next question. Methane has compressibility factor value of 0.9 at reduced pressure of 0.1, at reduced pressure of 1 and reduced temperature 1.5. For propane, the critical temperature and pressure are 369.8 Kelvin, 42.48 bar, respectively. The R is equal to 1.314 kilojoule per kilomole Kelvin. Applying the principle of corresponding state, the molar volume of propane at the same reduced pressure and temperature is. So we have to solve this problem. What is given? Read the last line of the question. It says at same reduced pressure and temperature. So we can apply. It is given here that you have to apply the principle of corresponding state. But since it is given that the propane and methane has same compressibility factor, same reduced pressure and temperature, so they are going to have same compressibility factor. So they have same reduced pressure and temperature, so we can find their real temperature based on this. Okay, so see here, PR is given, this is given. You have PC, TC for propane. So now apply the principle of corresponding state. It says that same pressure, okay, and like this. So for propane, pressure of propane divided by critical pressure is equal to 1, right? So pressure of propane is equal to 42.48 bar, right? And again, pressure of propane is equal to this, and temperature of propane divided by Tc is equal to 1.5. So temperature of propane is going to be something like this. Now we have the pressure of propane. Now we have temperature of propane. So can we apply the gas equation here? But we cannot apply the ideal gas equation here because it is given that the methane has a compressibility of 0.9, and since both the gas propane and methane they are at same reduced pressure and temperature, so they are going to have same compressibility factor Z, which is equal to 0.9. So you have to multiply the right hand side of the equation with Z. Okay, compressibility with Z. So we can find out the molar volume V divided by N. So V divided by N is going to be something like this. You have everything, you just put it, solve it. So you got V by N is equal to something like this, because you have put everything in SI unit. So you are going to get V by N in terms of meter cube per mole. But you were asked to answer this in meter cube per kilomole. So you have the value of meter cube per mole. You are asked to give the answer in terms of meter cube per kilomole. So you just multiply this with 10 to the power 3, and you will get this. It's kilomole, not mole. 0.99707 meter cube per kilomole. Now question number 5. The value of the compressibility factor at the critical point evaluated using van der Waals equation of a state is. So I have already shown you those values of it is asked. The question asked you to evaluate the compressibility factor at critical point. So compressibility factor is what? PV divided by RT. V is your molar volume, and in just few slides ago, we have derived what? Critical volume Vc is equal to 3b, critical pressure Pc is equal to A divided by 27b square. Okay, right? And your Pc is equal to this, and Tc is equal to this. So we have derived this now. Read the last line. Vc is equal to 3b, Pc is equal to A divided by 27b, Tc is equal to this. So you just have to put this here. You just have to put this here. So you just put this like this. This is P. This is your molar volume Vc. This is the value of RT. So this is going to, comes out to be something 3 by 8, which is equal to 0.375. So correct answer is your C. Okay. So you can rate, review, and recommend my slides and my lecture. And please share this. Thank you.